Now that we have the holonomy, the concept of holonomy, I want to introduce a simple property of the holonomy itself. Let's consider two curves that join at a certain point S. So here we have the curve gamma 1, which starts at the point S underlined, and then as we move along this curve, we reach the point S. Then starting from the point S, we have another curve that we can call gamma 2, and it goes all the way up to the point S overlined. Now there is a simple property of the holonomy. And by the way, we can call the union of these two curves just gamma. So the overall curve is gamma, and when we have S in here, gamma is equal to gamma 1, and when we have S in here, gamma is equal to gamma 2. It's quite intuitive. But if we act with the holonomy related to the curve gamma 1 from the point S underlined all the way up to the point S, and then we act again with the holonomy related to the curve gamma 2 from the point S to the point S overlined, well, a simple property tells us that this is equal to the holonomy related to the overall curve gamma from S underlined to S overlined. So this is just a simple property that I wanted to introduce related to holonomies. Now, I want to do something more interesting at this point. In particular, now we are going to consider an SU2 transformation. So this is a special unitary transformation in 2 dimensions. So basically we need a matrix V of x, a unitary matrix. You can think of this as a 2 by 2 matrix. And we transform the connection gamma A, gamma sub A of x in this manner. So the transformation gives us gamma sub A V of x, and we define it like this. V of x, then we have gamma sub A of x minus the derivative with respect to, so this is d over dxa if you want, so dA over I, and then we have V inverse of x. Now you might wonder why we need to introduce such a transformation. I want to show you that this is actually an important transformation because it will allow us to find those transformations that preserve the differential equation of parallel transport. Now, I want to show that. So I want to show you that starting from this transformation, the differential equation of parallel transport remains indeed invariant. So it does not change. The form of the equation does not change. Now we consider a spinor, Q of S, and we can define it to be V of x of S H sub gamma S underlined. H sub gamma of S underlined is related to the solution to the differential equation of parallel transport. Let me just remind you that if we consider the differential equation d over ds of chi, so last time we used chi for the spinor of gamma of S, this is equal to I gamma dot A of S gamma sub A of gamma of S chi of gamma of S. We can write the solution in the following manner. Chi of gamma of S overlined is equal to the holonomy related to a certain curve gamma, S overlined, S underlined, and then we have chi of gamma of S underlined, like this. So you can see that this H sub gamma of S overlined, S underlined is important because it tells us the solution. It gives us the solution to the parallel transport equation, if you want. But now we are not going to consider these two equations here. We will start from this expression, and just take the expression for granted at the moment. It is just an expression. So you have the holonomy, and here we have this transformation, this unitary transformation. We calculate the derivative with respect to s of q of s, and this can be written in the following form. So this is just the derivative of v of x of s with respect to s multiplied by h sub gamma of s underlined, plus v of x of s, and then we take the derivative with respect to s of h sub gamma of s underlined. Now we are going to rewrite this expression here simply as partial derivative of v of x of s with respect to xa, and then we have dxa ds, like this. And this is actually a total derivative because xa, the coordinates xa only depend on the parameter s, so we can also write it like this more appropriately, and this is defined as gamma dot a, which depends on s. Secondly, we can also rewrite the derivative with respect to s of this quantity. We have to remember the expression for h sub gamma because it is just a path-ordered integral. We have a path ordering of the exponential of I integral from s underlined to s ds gamma dot a of s, and then we have gamma sub a of lowercase gamma of s, like this. And when we take the derivative with respect to s of this, we get the same quantity because this is just an exponential, and we have to multiply that by the derivative of this expression here with respect to s. But when we take the derivative of this with respect to s, we are just going to get I gamma dot a of s gamma a of gamma of s. And this is going to act on h sub gamma of s underlined, like this. Therefore, if we put these results together, we can rewrite this equation like this. Derivative with respect to s, q of s, equal to, now we can factor out gamma dot a of s, and then here we have partial derivative with respect to xa, so we can write dA v of x of s plus I v of x of s gamma a of x of s h sub gamma s underlined, like this. Now this can be manipulated further. At this point in here, I'm going to put v inverse x of s v x of s, which is just the identity. So I'm simply inserting the identity in here, in this position here. And now I'm going to rewrite this in the following manner. So I have gamma dot a of s dAv. Now I'm not going to write x of s here for the sake of convenience. And then I'm going to put this v inverse in here. So I have v inverse plus I v gamma a, and I'm not going to write the dependence on x of s for convenience, v inverse, and then I have v h sub gamma, like this. And I can also rewrite this expression in the following manner. This is equal to minus v derivative with respect to xa v inverse. And why is this? Well, this comes from the fact that v inverse is equal to the identity, and if we take the derivative dA of both sides, this is just equal to the zero matrix, if you think about it. And therefore, from this equation, you get that this must be equal to this. It is just a simple computation. And therefore, we can substitute it there. And we can write the following. So we have gamma dot A of S, V, and then I have minus dA V inverse plus I gamma A V inverse V H sub gamma. But now you can see that VH sub gamma is just equal to what we define as Q. This is just Q of S. And if you also check, this quantity here is something that you should recognize from the transformation that we imposed for gamma. In particular, we can also factor out I. So if we put I here, we have to divide by I, and therefore in here we are going to get rid of this I. And at this point, you can see that we have something similar to this expression here. So we have V in here, gamma A, then we have V inverse on the right, and similarly we have this term minus dA over I, V on the left, and V inverse on the right. So this, if you check, is equal to I times gamma V A x of S, like this. And therefore, you can see that Q of S satisfies the following differential equation. D over ds, Q of S is equal to I gamma dot A of S, gamma A V x of S, Q of S. This is exactly the differential equation for parallel transport, and we know how to solve it. In particular, we know that the solution can be written in this form. Q of S overlined is equal to H V sub gamma S overlined S underlined Q of S underlined, where H V sub gamma S overlined S underlined is equal to path ordering of the exponential I integral from S underlined to S overlined ds gamma dot A of S, capital gamma VA gamma of S, like this. This is the expression. Now remember the definition of Q of S that we used near the beginning of this lecture, and I'm referring to this definition here. We can also write this as Q of S underlined equal to V of X of S underlined H sub gamma of S underlined S underlined, and it is quite obvious that H sub gamma of S underlined, that's just the identity operator. So if we go below, we can also rewrite this in the following manner. So Q of S overlined can also be written as V of X of S overlined H sub gamma S overlined S underlined, which is equal to H V sub gamma of S overlined S underlined, and then Q of S underlined, we saw just earlier that this can be written as V of X of S underlined. And this implies that the transformation for H is the following. So H V sub gamma S overlined S underlined is equal to V of X of S overlined H sub gamma of S overlined S underlined V inverse of X of S underlined. So this is the transformation for H. And if we take the trace of this transformation, we see that the trace is an invariant quantity. So the trace of HV sub gamma, S overlined, S underlined, is an invariant quantity. And this is actually very important because this is defined as the so-called Wilson loop, and it's an important quantity in loop quantum gravity.